My dear student, today I am going to talk about measurable function. So then I'll prove a small theorem, and I will explain what do you mean by a measurable function and the required background to define measurable function. Okay, so first, let us see what do you mean by a measurable function. My pen is all right. Okay, yeah. You see, so this is a let f be an extended real valued function. First, let me explain what do you mean by an extended real value function. Okay, let me explain what do you mean by an extended real valued function. Okay, so extended real valued function. Before defining extended real valued function, let us now talk about extended real number. In the set of real number, infinity, positive infinity, and negative infinity, they are not member. Okay, they are not member. Infinity and negative infinity, they are not member in the set of real number. So if we include these two number, then the resulting set we call it extended real number. Okay, and then the question is how to define the mathematical operation in the new set containing these two elements, positive infinity and negative infinity. So it is like that. If a is any real number, then addition of this with this positive infinity is always positive infinity. Okay, so a may be minus 1 billion, but if you add by positive infinity, it is infinity. Okay, then a negative infinity is also always negative infinity. This a may be plus 1 billion, 10 billion, 1 trillion, like that. Any real number, any big real number also you can take it. But still, if you subtract it by negative infinity, if you subtract by infinity, then the result is minus infinity. Okay, then a into infinity is either positive infinity or negative infinity. Okay, a dot infinity is either positive infinity or negative infinity. If a is positive, a dot infinity is always positive infinity. If a is negative, then a dot infinity is negative infinity. Okay, and this number a negative, it is undefined. Okay, it is not defined. It is not defined. Minus, what is the value of infinity minus infinity? It is undefined. No one knows it. It is undefined. This is not there. Okay, this should not happen. Okay, so this number is undefined. Also, 0 into infinity is also undefined. Okay, 0 also infinity is also undefined in the set of real number. In the study of real number, when you talk about extended real number, 0 into infinity is undefined. But particularly, especially for measure theory, by convention, especially for measure theory, by convention, 0 into infinity is in 0. Okay, 0 into infinity is 0. This is an exception, especially for measure theory. Okay, so in the set of real number, we include positive infinity, and minus infinity, and the resulting set we call it extended real number. Then the mathematical operation is like this. This is not allowed. This is not allowed. This is undefined, means this is not allowed. Okay, so that is called extended real number. Then a function is said to be extended real valued function if the function can take positive infinity and minus infinity also. If the function can take values positive infinity minus infinity also, and these operations are applicable and these operations are applicable. So that kind of function is called extended real valued function. Okay, so that kind of function we call it extended real valued function. Okay, so now let us go back to our slide. Yeah, let us go back to our slide. Yes. So f be an extended real valued function defined on a measurable set E. Okay, so f is a extended real valued function defined on a measurable set E. Then it is the definition of measurable function. Okay, then this function f, the function f, not the set. Okay, the function f is Lebesgue measurable function. So it is very lengthy, Lebesgue measurable function. So people used to prefer some brief name like just measurable function. Okay, we will use just measurable function. Okay, instead of Lebesgue measurable function we will use measurable function. Then f is a Lebesgue measurable function, or more briefly a measurable function. You look it here very carefully. If for each alpha, for every real number, so this alpha may be any real number, for any sort of real number, this set, this set, what is this set? Collection of those points such that f of x, the value of the function at those points is greater than alpha. Okay, e is greater than alpha. This is the collection of points such that f of x is greater than alpha. This is collection of points. If this set is measurable for each alpha in R. Okay, for each alpha in R, where alpha is any real number. Okay, for each alpha in R, if this set is measurable, then we say that this function is a measurable function. Okay, that is the definition. So what is a measurable function? For each alpha, the set x such that f of x is greater than alpha is measurable, then the function is a measurable function. Okay, so this is the definition of a measurable function. Okay, so now let us draw some diagram. What do you mean by this measurable function? Okay, just simple explanation. Okay, let us see, if possible let us try to draw some diagram. Okay, let us, yeah, suppose your function has value like this. Okay, all right, function is like this. So function is defined, yeah, like this. Okay, suppose this is alpha 1, and then this is alpha 2. So let it be here just alpha. So this set is, suppose this set is E. It is defined on this E. All right, so next let us use some other color. Let us some other color. Let me see where. Okay, blue. Okay, then this set is what? This is E. So let it be E2. So let it be E2. Okay, so if you take alpha, this is a real number, height from here to here is your alpha. Okay, so it means what? If this is x, this is x. If this is x, what is f of x? F of x is equal to alpha. Okay, then from the picture it is very clear. If you take x, this is your x now. If you take x somewhere here, okay, then f of x will be always greater than alpha. All right, f of x will be always greater than alpha. Right, so then what is, if you take alpha, what is f of x? Is strictly greater than alpha. This set x such that, okay, x such that f of x is strictly greater than alpha is equal to what? E2. Okay, E2. All right. So if you take alpha is this much length, no? Then those point of x, those point x such that f of x is strictly greater than alpha is your E2. So then suppose if you take, suppose if you take alpha like this here, this is your alpha, this is alpha. So from the graph, the function start from here and end here. Okay, from the graph, no value of the function is greater than alpha, no? Then x such that f of x is greater than alpha is what? There is no point such that f of x is greater than alpha. This is equal to phi. But phi is a measurable function. Phi is a measurable set. Okay. All right. So then, if you take alpha less than alpha 1, this is your alpha 1. Okay. From here to here, it is alpha 1. No? This alpha 1. But if you take alpha less than, if you take alpha less than alpha 1, then what is f of x? X such that f of x greater than alpha, that will be the set, whole set E will be there. Okay. So like this, for every real number you define, for every real number you find out this set x such that f of x is greater than alpha. Okay. My handwriting is not that good, but I think you can understand. So for every real number, such real number, you find out the set x such that f of x greater than alpha. So if that set is measurable, if that set is Lebesgue measurable, okay, for each alpha, if that set is Lebesgue measurable, then the function is said to be a Lebesgue measurable function, or just simply measurable function. Okay. All right. So that is the definition of measurable function. Now let us go to the theorem. Okay. So that is just after using the definition. Now we will use, we will prove the theorem, following theorem. So it is very simple, just using some knowledge of real analysis and set theory, and just using the above definition, we will be able to establish the following equivalent. Okay. Theorem. The following statements are equivalent. Okay. Let us see. The following theorems are equivalent. So f is a measurable function. Okay. Now we just define what do we mean by measurable function. Okay. So f is a measurable function. All right. F is a measurable function. Number 2 statement says that for each alpha x such that f of x is greater than or equal to alpha. In the definition, this equal to was not there, strictly greater than was here. Okay. In the definition of measurable function, so this equal to was not there, strict greater than was there. So here equality is included. For every alpha, for every real number alpha, x such that f of x is greater than or equal to is measurable. Okay. That means if the function f is measurable, then x such that f of x greater than or equal to alpha is also measurable for every alpha. This is statement 2. Then from statement 2 to statement 3, let us see, for all alpha x such that f of x is strictly less than alpha. Okay. So in the definition, f of x is greater than alpha, strictly greater than alpha. Now this one is what? X such that f of x is strictly less than alpha is also measurable. Okay. If the function is measurable, this statement is true. Okay. If this statement is true, this statement also true. Again, lastly, if this statement is true, this is also true. What does it say? It says that for all alpha x such that f of x is less than or equal to alpha, here strict less than was there, here equal to is included. Okay, is also measurable. Lastly, number 4 statement, we are going to, assuming that number 4 is correct, we are going to prove that the function f is measurable. Okay, that means if this condition is fulfilled, this is fulfilled. So the equivalence established. Okay, 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. That is the usual way of proving this equivalent. Okay, that means if this this can be regarded as a definition of the measurable function. Since these four statements are equivalent, so this one can be also regarded as a definition of measurable function. So each one of the statement can be regarded as a definition of, measurable function. Okay, so therefore in different textbook and different author use different definition. They are equivalent, okay, because they are equivalent. Some textbook may be using this as a definition of measurable function, some textbook may be using this one, some textbook may be using this one. Okay, they are all equivalent statements, therefore one of them can be used as a definition of measurable function. Okay, so now let us prove the first implication, that is 1 implies 2. 1 implies 2. 1 implies 2. What is 1? Statement 1. We have to assume statement 1 and prove statement 2. Okay, statement 1 is the function f, the given function f is measurable. Now we are going to say that statement 2 is okay. Statement 2 is also true. Suppose, let us assume statement 1 is true. Suppose f is measurable. Then let x be a point of this. That means what? If x is a member of this set, f of x is greater than or equal to alpha. Okay, so if x is a member of this set, I am using same symbol x here, don't get confused. Okay, x is a member of this set, then f of x is greater than or equal to alpha. So then what? F of x is greater than or equal to alpha. If f of x is greater than or equal to alpha, it is very clear from here, f of x is greater than or equal to alpha, then f of x will be strictly greater than alpha minus some other real number. If you subtract some number, then this will be smaller, no? So fx was greater than or equal to alpha, then f of x will be strictly greater than this one, because you have reduced by a quantity, by n quantity, 1 upon n. This is true for all n greater than or equal to 1. Okay, the strict equality will not be there. F of x will be strictly greater than alpha minus 1 upon n for every n greater than or equal to 1. So this statement is true for all n. If f of x is greater than or equal to alpha, then f of x is greater than alpha minus 1 upon n for all n. If this statement is true, this statement is true for all n. So that means what? X is a member of, x is a member of this set. When n is equal to 1, f of x is strictly greater than alpha minus 1. Therefore x is a member of x such that f of x strictly greater than alpha minus 1. Like that, when n is equal to 2, x is a member x such that f of x strictly greater than alpha minus 1 by 2. Like that. Okay, so you have sequence of set. This x is a member of all this set. Okay, then x will be also a member of all the intersection. No? X is a member of every set. Okay, then x should be member of their intersection. Okay, x is a member of their intersection is what? N going from 1 to infinity, this one. No? So that means what? Whenever you take one arbitrary point from this set, that point is also a member of this set. Okay, what does it say in set theory? This set is a subset of this set. Okay, this set, this set is a subset of this set. Okay, because if you take any point from here, that point is also here. So therefore this set is subset of this one. Now conversely, let us take one point from here. You take one arbitrary point from here, from this set, and let x be an conversely, let x be a point from here. You take just one point from here. That means what? X is a member of this intersection. Okay, that means x is a member of every member of this intersection, right? Every member of this intersection means what? If x is a member of that set, f of x is strictly greater than alpha minus 1 upon n, right? By definition, f of x is strictly greater than alpha minus 1 upon n for all n greater than or equal to 1. Okay, so from here you can simplify it. Alpha minus f of x is less than 1 upon n for every n greater than or equal to 1. So if this is true, as n tends to infinity, this numbers should be either less than 0 or equal to 0. Okay, all right, this is less than for every 1 upon n. Okay, for this is less than 1 upon n. Okay, for every n greater than or equal to 1. Therefore this should be either 0 or less than 0. That means alpha is less than or equal to f of x. Alpha is less than or equal to f of x. If alpha is less than or equal to f of x, means f of x is greater than or equal to alpha. Okay, that means x is a member of this set. Nah? So whenever you take an arbitrary point from here, that point is also a member of this set. Therefore this set is a subset of this one. So in one way we have proved that this is a subset of this one. In another way we have proved that this is a subset of this one. Therefore these two sets is exactly, they are exactly equal. Okay, they are exactly equal. All right, so what is the conclusion? What is the conclusion? So this set, the first one, is exactly equal to this one. Why? If you take any point here, that is also a member here. Okay, that means this is a subset of this one. All right, so if you take any point from here, that is also a member of here. That means this is a subset of this one. So one is subset of another one. Therefore the two sets are equal. This set, the two sets are equal. Okay, so by condition number 1, the function is measurable now. So therefore x such that f of x is greater than alpha minus 1 upon n. So alpha is a real number, minus 1 upon n is also a real number. Since the function is measurable, this set is measurable. Okay, by definition of the measurability, this set is measurable for each n. Okay, again by property of measurable set, if you have a sequence of set, measurable set, their intersection is also measurable. Okay, so intersection of all measurable set is measurable. So this is also measurable. That means since this is equal to this one, this set is also measurable for each alpha. For each alpha, this set is measurable. So that is statement number 2. Now we have established the first implication, 1 implies 2. Okay, assuming statement number 1, now we have proved statement number 2. Next, let us assume statement number 2. That means let us assume that statement number 2 is correct. And now let us prove statement number 3. Suppose, let us assume statement number 2. This is statement number 2. X such that f of x is greater than or equal to alpha is measurable for all alpha. For any alpha as you take, this set is always measurable. This is statement number 2. Then, so what is the complement of this set? Okay, if x such that f of x is greater than or equal to alpha, na, then the complement will be very clear. The complement will be f of x will be strictly less than alpha, because alpha equality was here, na? So this is the complement. Complement of this set is equal to x such that f of x is strictly less than. Okay, so what is the complement of this one? This one. Okay, this is very straightforward, you will understand. For all alpha, if you take any alpha, you take complement of this set, it is equal to this one, x such that f of x is strictly less than alpha. Okay, so again from the measurable set theory, we did it during our classes in the department. Okay, if a set is measurable, its complement is also measurable. Okay, so by statement number 2, this set is measurable for each alpha. Therefore its complement, it is equal to this one, is also measurable for each alpha. Okay, so this is statement number 4. Statement number 3. X such that f of x is strictly less than alpha is statement number 3. This is all measurable now. This is statement number 3. So from statement number 2, now we are able to establish statement number 3. Okay, so next, assuming statement number 3, let us prove statement number 4. See, what is statement number 3? Statement 3 is x such that f of x is strictly less than alpha. Okay, x such that f of x is strictly less than alpha for every alpha is measurable. Okay, if you take any alpha, then you define the set x such that f of x is strictly less than alpha. You define this set, the set is measurable. That is statement number 3. Okay, so that is statement number 3. Now we are going to prove statement number 4. So now, as we did in statement number in the proof first implication, in the proof of first implication, you can easily establish this equality. X such that f of x is less than equal to alpha is exactly equal to intersection n going from 1 to infinity, x such that f of x is strictly less than alpha plus 1 upon n. You can establish this equality. You can do it. Okay, this set is equal to this set. You can prove it as we did in the first implication. 1 implies 2. Okay, so let us see then in statement number 4 what we want to prove. We want to prove that x such that x such that f of x is less than equal to alpha is measurable for each alpha. Okay, right. So but this equality says that this set is equal to this one. Okay, but by statement number 3 this is measurable for each alpha and for each n. Okay, this is measurable by statement number 3. This is measurable. Again, by theory of measurable set, countable intersection of measurable set is measurable. Therefore, what? This set is measurable. Each member of the intersection is measurable. Therefore, their intersection is also measurable. So this is measurable. So this being equal to this one, this is also measurable. Hence, statement number 4 established. Okay, this set is measurable for all alpha. Okay, this statement number 4 is established. Lastly, we are going to prove 4 implies 1. Yeah, it is very straightforward. 4 implies 1. 4 implies 1. Suppose we are going to assume the statement number 4 means x such that f of x is less than or equal to alpha is measurable for each alpha. Okay, this set is measurable for each alpha. For every alpha, this set is measurable. That is statement number 4. We are going to assume this one. Now let us prove statement 1. What is statement 1? We are going to prove that the function f is measurable. Okay, we know that again here also we know that what is the complement of this set. What is the complement of this set? The set is x such that f of x is less than or equal to alpha. The complement will be, f of x will be strictly greater than alpha. X such that f of x is strictly greater than alpha. So this is the complement of this set 1. Again, by set theory, if a set is measurable, its complement is also measurable. Okay, since this set is measurable, its complement is equal to this one. It is also measurable for every alpha. Okay, for every alpha. So according to the definition of measurable function, x such that f of x is greater than alpha is measurable for every alpha. Therefore, the function f is measurable. Hence, f is measurable. Okay, thus we have established the 4 statements. They are equivalent. We have established the equivalence of the 4 statement. Okay, so today I don't want to speak too much. I want to give you some time also so that you digest whatever I have talked. This is a new definition for you, a new definition. Okay, so you have to read it and you have to watch it again and again. So try to clarify the concept. Okay, try to understand the concept very clearly, because this is new definition. So this has to be inside your brain. Okay, so the only way to digest it, you have to read again and again. You have to watch my video tutorial again and again. Okay, let me end here my 4th lecture. Thank you very much.